Welcome to Lecture 13, Section 2.5 of the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert Eyabi. Section 2.5, Congruence of Integers. Subsection 2.5.1, Definition. Congruence modulo n. Let n be a positive integer n greater than 1. For integers x and y, x is congruent to y modulo n, written as such if and only if x minus y is a multiple of n, i.e., we say that if n is a positive integer n greater than 1, then for every xy in Z, x is congruent to y mod n if and only if x minus y equals n times k, where k is an integer. Example: suppose A is congruent to B mod n and C is congruent to D mod n. Prove that A plus C is congruent to B plus D mod n. Proof: A congruent to B mod n, by definition, that means A minus B equals n times k1 for some integer k1, and call that equation 1. C congruent to D mod n implies C minus D equals n times k2 for some integer k2. Call that equation 2. Recall what we are trying to prove. We want to prove that A plus C is congruent to B plus D mod n, i.e., we want to prove that A plus C minus B plus D, all in parentheses, equals n times some integer k. I have equations 1 and 2. How do I get what I need? Add equations 1 and 2 and we get A plus C minus B plus D, all in parentheses, equals n into k1 plus k2, k1 plus k2 in parentheses. That breaks down to A plus C minus B plus D equals n times k wiggle, where k wiggle equals k1 plus k2, and that is an integer because the sum of two integers is an integer. By the definition of congruence, that means A plus C is congruent to B plus D mod n. So whenever you are told that x is congruent to y mod n, you immediately interpret that as x minus y equals n times some integer k. Here is a little problem for you to play with. If C times A is congruent to C times B mod n, and D is the GCD of C and n, where n is defined as D times M, prove that A is congruent to B mod M. N, M. A very interesting but simple proof. I will leave that as a simple exercise for serious students. Subsection 2.5.2 Theorem. The relation of congruence modulo n is an equivalence relation on the set of integers Z, i.e., if n is in Z plus n greater than 1, and the relation R on Z is defined by x related to y if and only if x is congruent to y mod n, then R is an equivalence relation. As a matter of fact, we've seen this before, but we dealt with x congruent to y mod 5 or mod 7. So for the first time, we are investigating this relation for an arbitrary positive integer n greater than 1. Let's go ahead and prove that R is indeed an equivalence relation. Let x, y, and z be arbitrary integers. We're going to verify reflexivity, symmetry, and transitivity. 1. Reflexivity. For every integer x, x minus x equals 0, and that equals n times 0, or n times k, where my k is 0. By the definition of congruence, that means x is congruent to x mod n. And by my definition of the relation R, that means x is related to x. And that means my relation R is reflexive. Symmetry. Suppose x is related to y. We must show that y is related to x, i.e., we have to show that y is congruent to x mod n. Or we have to show that y minus x equals n times some integer k. But x related to y implies that x is congruent to y mod n. And by the definition of congruence, that means x minus y equals n times some integer k1. Call that equation 1. Multiply equation 1 by negative 1, and we have y minus x equals n times negative k1, negative k1 in parentheses. K1 is an integer, negative k1 is an integer, call all of that k wiggle, then x minus y equals n times some integer k wiggle. And by the definition of our relation R is symmetric. Next, transitivity. Suppose x is related to y and y is related to z. We must show that x is related to z, i.e., x is congruent to z mod n, or x minus z equals n times some integer k. But x related to y implies x is congruent to y mod n, and that means by the definition of congruence, x minus y equals n times k1 for some integer k1. Call that equation 1. Also, y related to z implies that y is congruent to z mod n, i.e., y minus z equals n times some integer k2. Call that equation 2. Add equations 1 and 2 and we get x minus z equals n into k1 plus k2. K1 an integer, k2 an integer. The sum of two integers is an integer. So call k1 plus k2 k wiggle. That would be an integer. Therefore, we have x minus z equals n times some integer k wiggle. And by the definition of congruence, that means x is congruent to z mod n, i.e., x is related to z. This implies that R is transitive and hence it is an equivalence relation. Once more, we have just shown that the relation of congruence modulo n is an equivalence relation. So in a test or in a quiz, if I ask you to prove that the relation of congruence modulo n is an equivalence relation, I expect you to define the relation R as x related to y if and only if x is congruent to y mod n, and then proceed to prove that that relation is an equivalence relation. Subsection 2.5.3 Theorem. addition and multiplication properties. Now, congruences are very different from equations, but congruences actually do enjoy some of the properties of equations. And here are two of such properties. If x is an arbitrary integer and a is congruent to b mod n, then I can simply add x on both sides and maintain my congruence. In the same way, I can multiply x on both sides and maintain my congruence as if I was dealing with equations. Beautiful. Proof. We shall prove the second congruence. Suppose A is congruent to B mod n, then A minus B equals n times some integer k1. Call that equation 1. Multiply equation 1 by x. Then we have A minus B times x equals n times k1 times x. A, B, x, n, k1 are all integers. So right distributivity, associativity are all permissible. So by right distributivity on the left hand side, we have ax minus bx equals, and on the right hand side, multiplicative associativity gives us n into k1 times x. The product of two integers is an integer. So that implies ax minus bx equals n times some integer k wiggle, where k wiggle is k1 times x. But by the definition of congruence, that simply means ax is congruent to bx mod n, and that proves the second congruence. We leave the proof of the first congruence as a simple exercise for serious students. Subsection 2.5.4 Theorem. Substitution properties. Suppose A is congruent to B mod n and C is congruent to D mod n. Then A plus C is congruent to B plus D mod n, and A times C is congruent to B times D mod n. We already proved the first congruence in subsection 2.5.1. I'm going to prove the second congruence right now, and after I do that, I would like you to attempt an alternative proof for the first congruence. Suppose A is congruent to B mod n and C is congruent to D mod n. We want to prove that A times C is congruent to B times D mod n. Now, A congruent to B mod n and C an integer by theorem 2.5.3, A times C is congruent to B times C mod n. I can simply multiply both sides by an integer and maintain the congruence. Also, C congruent to D mod n and B an integer implies B times C is congruent to B times D mod n, again by theorem 2.5.3. I simply multiplied both sides by the integer B and maintained my congruence. But AC congruent to BC mod n and BC congruent to BD mod n, and the relation of congruence mod n being an equivalence relation implies that AC is congruent to BD by transitivity, and that proves the second congruence. Now see if you can do the same thing and give me an alternative proof for the first congruence. Subsection 2.5.6 Cancellation Law. Here is one of those properties of equations that congruences also enjoy, with a slight twist. We know that if ax equals ay and a is different from 0, then we can cancel a and end up with x equals y. What do we do if it is not an equation but a congruence? Is there anything like cancellation with congruences? Yes. If ax is congruent to ay mod n, and a and n are relatively prime, then I can cancel out the a and x would be congruent to y mod n. So cancellation is possible with congruences, but we must first check that a and n are relatively prime, i.e. their GCD is 1. Proof. Suppose ax is congruent to ay mod n and the GCD of a and n is 1. We must show that x is congruent to y mod n. But ax congruent to ay mod n implies that ax minus ay equals n times some integer k. But that simply means n divides ax minus ay. Factor out a, and that implies n divides a times x minus y in parentheses. And back to section 2.4, we proved that if a and b are relatively prime and a divides b times c, then a divides c. N and a are relatively prime and n divides a times x minus y. By this theorem, we can conclude that n divides x minus y, i.e. x minus y equals n times some integer k wiggle. But by the definition of congruence, that simply means x is congruent to y mod n, and we are done. Here are some 2 simple problems I want you to play with as we continue this lecture. Problem number 1. If a is congruent to b mod n, I want you to prove that a raised to the m is congruent to b raised to the m mod n for every positive integer m. 2. Prove that for every positive integer n cubed is congruent to n mod 6. Beautiful little problem. I'll leave these 2 problems as simple exercises for serious students. So far, we have mentioned a couple of properties of equations that congruences also enjoy. Another of such properties is what is known as linear congruences. If you have the linear equation ax equals b, a different from 0, then x equals b divided by a. What if you have the linear congruence ax congruent to b mod n? Can we solve for x? Is there a solution that would satisfy this linear congruence? Yes, but under certain conditions. If a and n are relatively prime, then the linear congruence ax congruent to b mod n has a solution in integers. As a matter of fact, we can say that if a and n are relatively prime, then this linear congruence has a solution in the integers that is non-negative and also less than n. And furthermore, any 2 solutions in Z are congruent modulo n. The proof is simple and straightforward, and I would leave that as a simple reading exercise for serious students. It's on page 103 of your text, Elements of Modern Algebra by Gilbert and Gilbert. Example: solve the linear congruence 20x congruent to 14 mod 63 if possible. Again, the first thing you want to verify is that 20 and 63 are relatively prime. If they are relatively prime, then that means a solution exists and we just have to find it. Using the Euclidean algorithm, we would find the GCD of 63 and 20. 63 equals 20 times 3 plus 3. 20 is 3 times 6 plus 2. 3 is 2 times 1 plus 1. And 2 is 1 times 2 plus 0. If you have forgotten how to execute the Euclidean algorithm, I will refer you to previous lectures. The last non-zero remainder in the Euclidean algorithm is our GCD. In this case, the last non-zero remainder is 1. That means the GCD of 20 and 63 is 1. Therefore, a solution to the linear congruence 20x congruent to 14 mod 63 exists. Now, let's find it. Now, if you do recall from previous lectures, we did say that if the GCD of A and B is D, then there exist integers m and n such that D equals AM plus BN, and we actually executed the procedure for finding m and n. That is exactly what we shall do in this problem. So, starting with the GCD, we make 1 a subject of this equation. 1 equals 3 plus 2 times negative 1. 2 is the next remainder. Solving for 2, we get 3 plus 2 becomes 20 plus 3 times negative 6, and there is a negative 1 out here. Write distributivity. That gives us 3 plus 20 times negative 1 plus 3 times negative 6, negative 1, and that gives us 6. 3 plus 3, 6, gives us 3, 7, plus 20 times negative 1. Remember from previous lectures, I said don't mess around with these remainders. Keep them as they are. They are very useful, and we would be substituting these remainders. Now the next remainder is 3. Solving for 3 in this equation, we get 3 equals 63 plus 20 times negative 3. So 3 becomes 63 plus 20 times negative 3, and there is a 7 out here. Plus 20 times negative 1. Open all of these up. 63 times 7. Negative 3 times 7 is negative 21. Negative 21 plus negative 1 is negative 22. Putting all of these together, we get 63 times 7 plus 20 times negative 22. So we have written the GCD as a linear combination of 63 and 20. Here comes the next step in the procedure. So far, the number 14 has not been used at all. Here is where 14 comes in. What I have is 1 equals 63 times 7 plus 20 times negative 22. I multiply all through by 14, and that gives me 1 times 14, which is 14. Negative 22 times 14, which is negative 308. I keep my 20. 7 times 14 is 98. So my new equation becomes 14 equals 20 times negative 308 plus 63 times 98. Observe that 63 is congruent to 0 mod 63. So 63 times 98 would simply be congruent to 0 mod 63. So all of these, the right hand side is congruent to 20 times negative 308 mod 63. Let's put together what we have done so far. Understanding that the relation of congruence is an equivalence relation which includes symmetry, that brings us to 20 times negative 308 congruent to 14 mod 63. Again, 20x congruent to 14 mod 63. What do we have? 20 times negative 308 congruent to 14 mod 63. Guess what our x is? X equals negative 308. This is our solution. But you may actually be required to find a non-negative integer solution that is less than n. In this case, less than 63. If that is the case, then you write negative 308 as 63 times negative 5 plus 7. And observe that 63 times negative 5 would be congruent to 0 mod 63, because 63 is congruent to 0 mod 63. So the entire right-hand side is congruent to 7 mod 63. So x equals 7 is a solution to my linear congruence where x is bigger than or equal to 0 and less than 63. This is my non-negative integer solution less than n. Subsection 2.5.8, System of Congruences. Just like equations where we have systems of linear equations, we also do have systems of linear congruences. If m and n are relatively prime, a and b are integers, then the system of linear congruences x congruent to a mod m, x congruent to b mod n has an integer solution. Furthermore, any two solutions x and y are congruent mod m times n. What do I have to check? M and n. If they are relatively prime, then this system has an integer solution. The proof can be found on pages 105 to 106 of your text, Elements of Modern Algebra by Gilbert and Gilbert, and I would leave that as a simple reading exercise for serious students. Example: if possible, solve the system of linear congruences x congruent to 5 mod 7, x congruent to 3 mod 5. Call this congruence 1 and call this congruence 2. The first step would be to verify if 7 and 5 are relatively prime. That is easy because both 5 and 7 are primes, so yes, 5 and 7 are relatively prime. So a solution exists. How do we proceed to find the solution? Here is the procedure. We start with congruence 1. X congruent to 5 mod 7 implies that x minus 5 equals 7 times some integer k. Solve for x. X equals 5 plus 7k. Call that equation 3. Now substitute equation 3 into congruence 2, and we have 5 plus 7k is congruent to 3 mod 5. By one of the properties of congruence we proved above, add negative 5 on both sides of this congruence and you would maintain your congruence. And that leaves you with 7k is congruent to negative 2 mod 5. But 7 is congruent to 2 mod 5. So 7k reduces down to 2k congruent to negative 2 mod 5. 2 and 5 are relatively prime. So by the cancellation law, I am reduced down to k is congruent to negative 1 mod 5. We are always interested in non-negative integer solutions. So negative 1 is the same as 5 times negative 1 plus 4. 5 times negative 1 is congruent to 0 mod 5. So that leaves us with 4 mod 5. So k is congruent to 4 mod 5. But again, what is x? X is 5 plus 7k. So in the place of k, substitute in 4, and we have x equals 5 plus 7 times 4, which is 33, as the solution to the system of linear congruences 1 and 2. Furthermore, x congruent to 33 mod 7 times 5, or x congruent to 33 mod 35 gives all solutions to the system of linear congruences. Subsection 2.5.9 Chinese remainder theorem. This is simply a generalization of a system of linear congruences. Let n1, n2, n3, right up to nm be pairwise relatively prime. Then there exists an integer x that satisfies the system of linear congruences. X congruent to a1 mod n1, x congruent to a2 mod n2, x congruent to a3 mod n3, right up to x congruent to am mod nm. And furthermore, any two solutions x and y are congruent modulo n1 times n2 times n3 times nm. You can see that indeed it is a generalization of a system of linear congruences. Let me give you a little example. The proof is left as a simple exercise for serious students. Here is an example. Solve the following system of linear congruences if possible. X is congruent to 5 mod 7, x is congruent to 3 mod 5, x is congruent to 2 mod 8, x is congruent to 2 mod 3. The first step would be to verify that 7, 5, 8, and 3 are pairwise relatively prime, and then apply the strategy that we used in 2.5.8 repeatedly for all the congruences, and then end up with your final x, which would be the solution to the system, or the x value that satisfies the system of linear congruences. I would leave that as a simple exercise for serious students. It may be a little bit long, but not impossible. That brings us to the end of section 2.5, lecture 13. God bless you. Thank you.